Hey, what's up, guys? Yeah, so welcome to my real analysis. The mathematical analysis video. And this is all my previous video about the mathematical analysis. There are 40 of them. And today I want to add some interesting topic called the Baire Category Theorem. This theorem is interesting that I remember that I heard when I was undergrad, but I didn't understand the detail. So I want to present the idea and the proof. Hope you guys subscribe to my channel. Okay, so let me just introduce this. So this is also a theory in the topology, which I hope I can film the basic topology in the future. Okay, but let me just make a recall. Okay, so define. So let's say your Z and D is a matrix space. Okay, and when I say E is a subset of Z, is a nowhere dense. So you can view the nowhere dense is like the set which is if you take the closure, there's no open subset. So idea is that if the closure of E do not contains any non-empty open subset. Okay. This is called nowhere dense. Okay. And so this theorem just is this. Suppose Z and D is a complete matrix space. So the idea is that if you have the complete matrix space, then every Cauchy sequence will converge by definition, and this will make your space cannot be written as the countable union of different nowhere dense subset. So ZD is a complete matrix space. Then the Z cannot be written as the summation union of En, where En is nowhere dense for every n. Okay. Okay, so this is the theory. Okay, so this theorem is very interesting that it has some applications. Okay, then we need to prove this. And this theorem proof techniques like the same as somebody want to prove the non-empty perfect set must be uncountable. So it's the same technique. Okay, so in order to do this, let's prove this lemma. So this lemma is also interesting. So the idea is that this guy is a complete matrix space. Complete matrix space. And let's say Vn for each n is a dense open subset. Then a dense means that the closure of the space is the same as Z. Then what? Then the union of this is non-empty. Okay, this is a very standard proof. Yeah, this is very standard proof. So let me just make it ideal. So the idea is that let's say imagine that you have this space, right? And then you can pick up any, let's say you choose x1 belongs to V1, right? So this is V1, right? And then you choose a point which is x1. Okay, and you draw a ball which is R1. V1 is open. Okay, so there is a R1. You can choose R1 less than 1 such that the BR1 x1 is in V1, right? So this is the step 1. So step 1 is trivial. Okay, and the this guy is open, and the V2 is also dense, right? So you know that V2 is dense. So you know that the V2 intersection with this BR1 x1 must be non-empty. And this guy is open, right? Because BR1, this open ball is open, and this guy is open, right? So that means you can find x2, so you can choose x2. Okay, such that x2 belongs to V2 intersection BR1 x1. And there is a okay, so you can choose. Let's say this is x1, right? This is R1, and you choose x2 here. Okay, and you want to make x2 smaller, such that smaller that x2 and x1 distance do not touch. Basically, you want to make this distance less than half, so they do not touch. Okay, so you can choose. So this is open, right? So you can choose R2 less than half. such that this BR2 X2, you want to make this whole set sit in this V2 sit in this V2 intersection BR1 X1. And you can always make it because this guy is open. Okay. So right, then you can do a third step, do the same thing since V3 stands. Right, so you can make X3 belongs to V3 intersection with this BR2 X2. But now you need to change the R3 to be less than 1/4, such that BR3 X3 is complete C inside this V3 intersection with BR2 X2. Okay, so you can keep doing. Okay, you can keep doing. So you get X1, X2. Okay, which satisfies three properties. First 1, 2, and 3. Okay, so first one is trivial, right? First one is BR and XN less than VN. This is trivial by my construction, right? Because BR to X2 less than is a subset of V2. BR to X3 is subset of V3. Okay, so this is trivial. And you can, by my construction, right? I can also make it. I can also make this BRN plus 1, XN plus 1 closure less than this BRN XN. This is also my construction, right? I can make it smaller so you do not touch. So if I take closure, it will sit inside this. So this BR2 X2 will less than this BR1 X1. Okay, and finally, this Rn is less than 1/2n minus 1 for n1, 1, 2, 3. Okay, so it's easy to check that, right? So by this construction, you know that the xn plus 1, the xn is less than 2 to the 1 to the n. Okay, so you can use your simple mathematics. You can check that if you want to compute that this xn plus 1, x2, so xn plus 2 up to dx something. Let's say dn plus k. Let's say you go to xm. Right? You can bound this guy by arbitrary small if you choose n and m to be arbitrarily large. So which just means that this can be arbitrarily small. So which means that this all xn and from 1 to infinity becomes a Cauchy sequence. Okay, so and the original, I assume that this ZD is a complementary space. So there exists. So if you take the n xn go to infinity, you converge to some point x, which x belongs to z. Okay, now but so this x is a limit point, right? And by this, right? So this x is limit point. So which tell you what? Which tell you that x must belongs to the Rn xn, right? For each n. Right, for each n. Right, because each xn belongs to this Brn, and and its limit point becomes in its closure, and this Brn closure xn is a subset of Vn. So which tell you that if you go from n from 1 to infinity, which is empty, non-empty, right? Because for each n, for each small ball, there's a point x which lies in every n. So if you take the all intersection of this Vn, which gives you non-empty. Okay, so this is our lemma. So once we have this lemma, then we can easily to prove. So let's prove original Baire category theorem. Let's call it BCT. So by contradiction, suppose Z is a union of En, where En is nowhere dense. You can take the closure. So Z take the closure is the same as Z because Z is the total space, and then you can take the closure of it. And then you take the complement, which okay, you can take the right. You take a complement, right? So you say the complement of all space you get empty is the same as the all intersection of this En bar closure. Okay, so this En bar is a closure, right? So this is closed. no, and closed do not contains any open subset, right? And then you take the complement. So nowhere dense take the complement will be open and dense. This is you can check. This is very simple, right? So which by contradiction, right? Because now this En bar closure is an open and dense subset, but their intersection is not empty. Okay, so this is a proof by using the lemma. Okay, so using lemma. This is exactly the same thing as one want to prove that the perfect set is uncountable. If you haven't seen this video, you can go to my play. You can check out my playlist. Okay, so there's one applications which I think is also interesting. So this states that suppose your A is a 0, 1 intersection with the intersection with the irrational numbers. So basically A is just irrational number in 0, 1. Okay, so it's just irrational in 0, 1. And A cannot be written as the union of Fn, where Fn is where f of n is closed. Well, this is really weird. That very difficult to prove if you haven't noticed theory. Okay, so proof is very simple, right? Because we have the list BCT. So suppose A is a union of the closed, right? So the irrational number is nowhere dense, right? So which tell you that f of n is nowhere dense. And you can union with all the rationals, right? Because the rationals are countable, right? So you can take out all which are is rationals, which you take do the union. So this guy will be 0, 1 because this is original is irrational is 0, 1, and you take 0 all the rationals so become 0, 1, which is and the single point is nowhere dense, right? So this guy become the union of nowhere dense. Contradiction with BCT. Okay, so this is a very interesting application. Okay, that's it. See you guys next videos. Hope you guys subscribe to my channel.